The first unit that we'll be learning about in Chemistry 2 this fall is on reaction rates. And a reaction's rate describes how quickly or how slowly that reaction progresses. The rate of reaction can be important because of many different reasons. For example, if you worked in the chemical industry and it was your job to make a particular chemical for a consumer product, you might find that too fast of a reaction could cause some serious safety hazards for your company. On the other hand, if you are just a regular person, you still are concerned with the rate of reaction because of something called better living through chemistry. For example, everybody has a refrigerator at their house. The purpose of a refrigerator is to slow down the reaction of your food spoiling. So we're controlling the rate of reaction so we can eat our food longer. Another example of that would be getting a special coating on your car to slow down the rusting of your car. You're trying to control the chemical reaction rate of the rusting process. We define a reaction rate as being equal to the amount of chemical that is used or produced divided by the amount of time the reaction takes. The amount of chemical is usually measured in moles and time in seconds. So chemical reaction rates are typically given as moles per second. One note about the numbers of reaction rates and what they mean. If a reaction takes less time, that means it has a faster or a greater rate. So to give you an idea of how the numbers work, let's compare that to measuring your rate of speed in a car. If you're traveling at 60 miles and you travel those 60 miles in 1 hour, then your rate of speed is 60 miles an hour. But if your trip takes more time, that means you have a slower or a lesser rate. So perhaps you're traveling those 60 miles in 2 hours, which would give you a rate of 30 miles per hour instead of 60. So when you see a lower rate, that means the reaction takes longer. When you see a higher rate, that means the reaction goes faster. We can explain how reactions occur and how they are affected by the rate of reaction by using something that's called the collision model. And we've talked about this before, we just haven't given it a name. So these ideas should seem vaguely familiar to you. The collision model can be used to explain why and how do reactions occur at all, and how is that related to how fast they go. The first part is that reactions occur by molecules colliding with each other. If molecules don't collide, you don't get a reaction. Some of these collisions are violent enough to break the bonds in the original molecules, and then the reactants can rearrange to form the products. For example, let's say we started with the molecule BRNO, and you can see by the G that it's a gas. Remember that from last year. This reaction happens to be a reversible reaction. See the half arrow going each direction? It means sometimes this reaction can go forward and sometimes it can go backward. We're going to look at the forward case. So the molecule BRNO can sometimes break apart into NO gas and bromine gas, Br2, remember Brinkelhoff. And of course, we got to balance our equation. Now let's look at the molecules. Here are two molecules of BRNO. If these two molecules are going to react and break apart to make our products, we have to have a collision. And that collision has to have enough energy, or it has to be violent enough to break the original bonds in this molecule. So you have to have a high-speed approach. If there's enough energy in that collision, the bonds between the bromine and the nitrogen will start to break, and as a result, that gives a chance for the bond between the bromines to start to form. So the energy of the collision breaks the bonds between the bromine and the nitrogen, giving the molecules a chance to rearrange themselves, or giving the atoms a chance to rearrange themselves, and you get this bond forming between the two bromines. So then you end up with 2 molecules of NO and 1 molecule of Br2. The bromine-bromine bonds form. We can also use the collision model to explain the factors that affect reaction rates, and you've been learning about these factors since we started this year. There are 4 factors that affect reaction rates, and we'll use the collision model to explain why and how they affect reaction rates. The first one is concentration. Last year we defined concentration as moles per liter. You can think about it this year for reaction rates as though it was molecules per space. How many molecules in how much space? If you look at this picture over here, just as an example, it looks like there are a lot of people crammed into a small amount of space. What would that do to the number of collisions between those people? Think about the hallways, right at the end of the day or on the way to lunch. Lots of people in a small amount of space means that you have more collisions, and more collisions is going to make your reaction go faster. So you have a higher reaction rate. Higher concentration, more molecules in the same space, more collisions, higher rate. The second factor that affects reaction rates is temperature. Remember from last year, temperature measures kinetic energy. Reaction rates increase when temperature increases. But why? This has to do with an idea that we haven't talked about yet. It's called activation energy. Each reaction has to have a certain amount of energy, or its molecules have to have a certain amount of energy before that reaction can take place. And that's called the activation energy. It's the minimum amount of energy needed for the reaction to occur. And the symbol that we use for that is a capital E and a lowercase a. How much energy do you need to get this reaction to go? Now that we know what activation energy is, we can talk about how temperature affects reaction rate. Each reaction has its own activation energy. It has its own energy requirements. And some energy requirements are high enough that the molecules don't have enough energy on their own to make that reaction occur. They need a little bit of extra energy before they can react. That extra energy can come from increased temperature. So here's our reasoning. Higher temperature, remember that's kinetic energy, so that means higher speeds on the molecules. That means more high energy collisions, which results in more broken bonds and faster reaction rates. The third factor that can affect a reaction rate is called a catalyst. You've probably heard of a catalytic converter in your car. A catalyst is a substance that speeds up a reaction without being consumed. That means it's not a reactant, it's not a product, its only role in the reaction is to make it go faster. An example of a catalyst would be the enzymes that are found in your stomach. Enzymes in your stomach help to break down the food that you eat so you can digest it more efficiently. little bit more about catalysts next week. The last factor that can affect the reaction rate is the surface area, or the amount of area exposed of the reactants that you're dealing with. If you increase the surface area, more reactants can collide, and that causes an increased rate of reaction. This is the exact same idea as when we talked about surface area with solutions. The higher the surface area, the faster the substance dissolves. It's the same exact idea. More surface area is exposed, that allows for more collisions, which allows for a higher rate of reaction. You'll learn about this a little bit more in detail this week when you read the article about the grain elevator explosion, which has a lot to do with surface area because of the very fine dust and powder that used to be a problem building up in kind of old school grain elevators. So that's it for today. Congratulations on completing your first homework assignment.